So my name is Ben. I'm the Raspberry Pi Community Manager working at the Raspberry Pi Foundation in Cambridge. I'm the creator of GPIO Zero, a Python library for interacting with the GPIO pins on Raspberry Pi, which I'm going to be talking about in the talk. I write a column for opensource.com, a community project that does all sorts of tutorials and articles and things, and so it's well worth checking out. There's lots of great material on there. There's my GitHub handle and Twitter handle on there as well, and you can reach me by email. So we've sold over 14 million Raspberry Pis around the world now, so things are going really well. So I mean, I was looking back at some of the slides I made the first EuroPython I spoke at, and we were sort of about 3 million at that point, and that was seeming really big, and really like we've made a real big impact in the early days, and it's great to see how far we've come. And similarly, the actual number of staff on the foundation team has grown rapidly over the last couple of years, and there was a slide I had with 3 or 4 people that were the foundation at the time. And now we've grown to this is from just a week or so ago. We had an all staff to get together, and it's great to see all the great things that we've been doing. We were founded in 2009. We only started sort of hiring people around 2011, 2012. The Raspberry Pi Foundation incorporates 3 organizations now. The trading company that makes and sells the Raspberry Pi computers. There are people who work in the foundation that are sort of purely on the education side of things, but then there's also Code Club and Coder Dojo, 2 sub-organizations that we run in providing opportunities for young people to get involved in programming, learning about technology, learning about computers and digital making all around the world. The Raspberry Pi trading company operates as a way to feed their profits into funding our educational programs. That's how our business model works, and it's doing really well, as you can see. The Raspberry Pi Foundation's mission is about putting the power of digital making into the hands of people all over the world, so that people are capable of understanding and shaping an increasingly digital world, able to solve problems that matter to them, both as makers and entrepreneurs, and equipped for jobs of the future. Now, that doesn't just mean people learning to be software developers, go and work for Google and Intel and people like that, but actually preparing people for a better understanding of technology, whatever field they end up going into work in. And we do this by providing low-cost, high-performance computers. We run education programs and do a lot of outreach activities. We provide free resources for everybody, and provide teacher training, both in person, so people can apply to come on one of our training courses, and we actually deliver training online, so anybody can join in. We're not limited to the number of people delivering the training in the team. Take a look at the current models of Raspberry Pi. Again, this is something we've come a long way since my first EuroPython talk, but the Raspberry Pi 3 is our sort of main headline product. It's a 64-bit quad-core ARM v8 running at 1.2 gigahertz with a gig of RAM, and that's our $35 product. The main product that we sell has always been $35, so over the years we've improved the quality and the power and the spec of that main headline device, and this is but keeping the price the same. So that's where we've got on the main product. A couple of years ago we introduced the Pi Zero, which is a $5 version of the Raspberry Pi. It uses the Raspberry Pi 1 chip at a faster clock speed. So you've got a gigahertz there rather than the 700 meg that the original Pi ran at. It's got half a gig of RAM, and that one's, as I say, that one's $5. Not as powerful as the Pi 3, but certainly really useful in certain maker products and projects that you can embed something you want to embed the Pi inside. We recently introduced a $10 variant which has Wi-Fi and Bluetooth, so a lot more scope for connectivity in your projects as well. So that's where we're at on the product side. And in terms of the software, so again, in sort of 2012 when the Pi came out, we were in a place where we had a sort of bog standard LXD theme, looked really, really traditional Linux desktop, and we've done a lot of work recently on improving that and making that skin look really nice but still be really performant. It's a very basic sort of thing. There's no 3D acceleration or anything special going on there. It's just doing what it does well, providing you with access to the education tools and some of the software and things in there. It's looking really nice set of icons and things. We also recently released this operating system for desktop PCs. So we provide an x86 image you can download. You can run in VirtualBox or stick it on a USB stick and actually run a live image on a laptop or PC or Mac. So you can actually boot this up and get the sort of near enough the same experience you'd get in terms of software on the Raspberry Pi without the additional hardware and the physical computing I'm going to be talking about. But actually get access to things like Python and other software tools and other programming tools in this isolated environment that you can boot from a USB stick. And if you really like it, you can install it as your main operating system. We've talked for a long time about moving on from IDLE, which is the main education-focused editor provided. It's actually sort of bundled with Python if you download Python from the Python website. So we've talked about for a long time about moving on from this and finding a replacement, finding something more suitable. As an intermediate measure, we've introduced a new IDE called Thonny, which is now pre-installed in Raspbian. IDLE is still there, as a lot of textbooks and things sort of point to that, but and it does work to a certain extent, so it's still useful. But there's an alternative there. It's a Python 3 only editor. There's no options, which is really helpful for education. And it's got some great debugging tools and various other features. But on the longer term, we're investing in developing the Mu editor that Nicholas Tolliver has been working on. So we're working with Nick with a list of specifications from our feedback from teachers and some of the teachers that we have on staff that are feeding into what a Python editor should look like for education. And it's something that kids and teachers will start with, and they may move on to more complicated, more complex IDEs, more powerful tools, but we hope that this is a great start. You can read about that on Nick's website as well. So going into physical computing, so the main aspect that makes the Raspberry Pi different from regular computers is the GPIO pins. That's the general purpose input-output. There's a bank of 40 pins, and you can see there's a little port label there that labels the pins. They all have different purposes. So physical computing is all about connecting up flashy lights, motors, robots, sensors, photo, video, and enabling you to get into the Internet of Things, do home automation, and physical projects. So if you take a look at that bank of GPIO pins, this is what it looks like. This is a little handy guide from a website called pinout.xyz, which is a really useful reference if you're hacking with a Raspberry Pi. So there are mostly 3-volt pins. There's 2 5-volt pins. If you want to do something with robotics and motors, you'll probably want a 5-volt supply. The GPIO pins are all numbered, so you can individually trigger certain pins by their number to go high or low. And they're variable 3v3, they're 3.3 volts. We also provide, there's also a set of other protocols you can use that for high-speed data transfer buses and things like that allow you to do more complicated than just turning individual pins high and low. You can actually do a lot more by sending data high speeds down the pins using these different protocols. So there's various ways you can sort of access the pins. You can either wire things directly to the pins or use a breadboard. Actually make up your electronic circuits by connecting things directly to the pins using jumper cables. So you can do something like this. And people also make accessories that that actually place on top of the pins that sit neatly on, a bit like an Arduino shield if you're familiar with that kind of thing. We have this standard called HAT, which means hardware attached on top, and it's for the 40-pin header, and it sits neatly on the Pi with mounting holes in the right place, and it's designed to just be a sort of neat sort of standard way of providing add-ons. And there's also you're expected to have an EEPROM on a hat, which is a way of, you can program a device to tell the Pi, tell the device tree what is attached so that it can do something according to what hardware is attached. So if you used any GPIO in the early days of Raspberry Pi, there's a library called RPi GPIO in Python. There's a very low-level library, and it was used for 3 or 4 years as the sort of main way, the canonical way of doing GPIO programming, from everything from flashing LEDs to robotics and sort of IoT home automation stuff. It's quite verbose, lots of boilerplate code, and so one of the things that I worked on was this GPIO 0 library, which abstracts away the components and the devices into these classes that you can easily write code which talks about what you're doing with the devices rather than what you're doing with the pins. This makes it a lot easier, so you get something like this rather than the sort of sending pin numbers that you keep passing around, high and low. Actually talk about what you're doing to the device, in this case the LED. And then you even get into things like this, where you have a threaded blink, you have a blink thread sort of running in the background, which just means you can hack on more devices much more easily and get going with your project. The GPIO 0 library supports all sorts of different devices, everything from sort of basic components, buttons, LEDs, ultrasonic distance sensors, analog digital converters, remote control sockets, traffic lights, and robots, and motors, servos, and a few different sort of bespoke hats and add-on boards that we provide composite device classes for. So there's a great, this isn't even in the latest version actually, but the device hierarchy in GPIO 0 is quite interesting. It's all in the documentation if you want to take a look. So one of the great things about the way that GPIO 0 allows you to get started is you can start with really simple code that's very easy to read and write and understand. So if I wanted to get an LED connected up to a button so that the button actually activates the LED, and I'm starting with a child or a teacher who's doing this for the first time, I would show them to write something like this. It's very simple to understand procedural code. You can progress onto other paradigms. So looking at event-driven programming, you do the exact same setup where you've created your LED, you've created your button, but you have it fire off these events based on when these things happen. So when the button is pressed, it fires the LED.on method. When released, LED.off. And then you can go off and do something else. You're not stuck in a while loop. And you can even progress onto an even shorter version of code where you're using the declarative paradigm. And again, all of this just happens in the background in threads. Setting the source of the LED to the button, the values of the button, does the exact same as both of these other examples. But it's in a declarative way, you've declared in one line how the devices should behave. And there's some really interesting stuff you can do with this paradigm. So just to explain how that works, if we got a device like a PWM LED is actually just a regular LED that you configure to use pulse width modulation to control the brightness rather than just turning it on and off. And if we inspect LED.value, we can see that that's 0. So rather than being true or false like a regular LED would be, a PWM LED has a 0 to 1 value, which is the level of brightness. If we run LED.on, we actually change that, and then we inspect the value. It's now changed to 1, but you can also set that to 0, which will do the same as running LED.off. So that's what .value is. And what you find is that if you have two components that have the same value set, so like 0 to 1, so a potentiometer connected to a rotary dial connected to an analog digital converter chip, the MCP308, they both have a value 0 to 1. So things like LED and button both have true-false values. You can pass one into the other. So doing this, LED.value equals pot.value sets it once so that the LED brightness matches wherever the dial is at that given time. And what you end up doing is writing while loops like this to say, I always want the LED to be, the brightness of the LED to be controlled by the potentiometer. And so this is where the source values thing comes in. So everything has a dot value, whether it's an input or an output. And then they also have a dot values, plural, which is a generator, it's just a generator constantly yielding the current value. So every time you ask for it, the next one you get the dot value. Devices that can have their state set, their value set, have a dot source, and that's just a way of saying, where do I get my values from? So you can pass in, like the most obvious case is to pass in the dot values, because it just takes any iterator, so in this case an infinite generator yielding the value of the device into the other device, and it just means that they're connected, which makes this work. You can also process values in between as they come out of one device into the other. So you can write your own function to do something in between. We also provide a set of commonly used tools, so things like negated is an easy example. So negate the Boolean value as it comes out of the button, pass that into the LED. It means you have reverse logic of when the button is not pressed, the LED is on. When the button is pressed, it's off. You can also combine values. For instance, if you have 2 buttons and an LED, and you want the LED to be on if both buttons are pressed, then you take both sets of values and them essentially using this all values function. And you can do this with any number of devices. And as long as all of them are true, or both of them in this case are true, then the LED's value is true. So a really neat way of creating an AND logic gate using GPIO components and just a few lines of code. A couple of other examples using the same sort of paradigm. We have an LED bar graph class. So that's the idea that you would have several LEDs in a row, and as well as just being able to, there's a class called LED board, which is just a series, an arbitrary series of LEDs. LED bar graph is one where you can set its value from 0 to 1, and rather than arbitrarily index LEDs, you set the value 0 to 1, and it lights up that many LEDs up to the maximum. So if you set it to 0.5, half of them will be up in a bar graph sort of sense. And so we have another class called CPU temperature. So there's a few classes in the library that are what we call internal devices rather than sort of GPIO components, but they have the same properties and they can connect up to other devices. So CPU temperature, you can read the temperature, like it's a temperature sensor, actually get the Celsius value. But you also get a dot value of that, which is a 0 to 1 on the scale that you've provided on the init. So if it's halfway between 50 and 90, for instance, then your LED bar graph will be half lit, and you can see that go up and down as you do different things on the device, as the CPU temperature is going up and down. And similarly, one called ping server, which just runs a ping and returns a true or false value of how the ping went. So you create a ping server on google.com. Another thing you can do is set the source delay, which means how often it goes and looks for the next value. If you don't want to be pinging Google as many times as you would be reading a potentiometer value or something. If you just want to do this once a minute, you'd set the source delay to 60. Set the value of the green LED to equal the Google values, and set the red to be the opposite of the green LED. So as well as doing negated Google values, instead of negated Google values, I'm just negating the actual LED rather than looking at that up twice. So either the green is on or the red is on according to whether it can ping Google successfully. Just a little status monitor. There's an add-on board called Energini, which is a little remote control socket the add-on board talks to via radio. This is, at home I have a pet tortoise, and this is another internal device class, the time of day, that you set up and say, this time of day is active between 8 a.m. and 8 p.m., and then you say that the lamp, which is connected to the Energini socket, should be on between those times. And again, you could use the procedural paradigm for this and just say, while true, keep checking, or something like that, or use the event-based, that when this time is activated, then run this function, but this is another way of doing it. Another thing that we do is support multiple pin libraries. So when I said before about RPi GPIO, this was the one that people were choosing to use. So previously, if you wanted a different, if you wanted to use a different library because it had a specific feature that one of the other ones didn't, you would have to rewrite your code into that library. What we do is we provide multiple backends. So you just elect which pin library you use, and you get the features of that library. So RPi GPIO is the default. It's sort of the most commonly used and in some ways the most stable. That's installed by default in Raspbian, so that's the one that's by default elected to be used. There's a couple of others, other GPIO libraries that we support. And we also provide a native pin implementation, which is kind of experimental, but it works for basic things. But it's fallback if you haven't got anything else. And there's also a mock interface, which we use in our test suite, but it is quite handy for being able to just test that your code is sort of valid. And both of these, the native and the mock pin, are included in the library. You don't need an extra module like you do with the others. So PyGPIO is one of the libraries. It's implemented in C and runs as a daemon on the Pi. It will allow remote socket connections that control the GPIO pins. So using the GPIO API and the nice code you can write, you can actually control a Pi over the network and actually run this from your PC, as GPIO could be installed on any machine because it can be used in this way. It doesn't have to be a Raspberry Pi, but it can control the GPIO pins of a Pi using the PyGPIO daemon. And so, for instance, there's one way of doing it, is if you use the PyGPIO factory to create a sort of connection to a Pi that has the daemon running. And rather than creating an LED just on a pin number, you associate it with that device, so with that pin factory, and then the rest of the code is exactly the same. And alternatively, with some code that would, like on the right here, that would be used normally for using the pins directly on the Pi, you can actually, so yeah, with that exact code that unchanged, just with some environment variables set, you can actually have it execute the GPIO commands over the network. So you could change that the IP address there before you run it again, and it would execute the same code unchanged on a different device. Here's just an example of using mock pin. So I do this quite a lot on my laptop just to test that some code over it and some documentation or something is accurate. So if you launch the pin factory mock and then open your Python shell, you can import something from GPIO, create an LED. Here's an example where I've just said led.blink. I've inspected the value, and then a second or so later inspected it again, and you can see that it's in the background. It's doing all the things that the devices should be doing. And as I say, we use this in our test suite, but it is quite handy just to be able to test your own code without wiring up components. Another thing you can do is you can drive the input pins. So if you created a device which is using an input pin, you can tell it, because there's no way of telling it that there's no way of actually pressing a button that you've created in that's connected to a mock pin. But if you access the pin and drive it high or low, you can actually affect the state of that button. So again, this is how we test things in the library, but really handy just to be able to test out. So in the next release of GPIO, we'll come with this handy pinout command line tool as well. So one of the things we do is inspect the device you're on, to sort of find out some information about it and what sort of pins you have, what hardware you have, and allows you to do, will warn you if you can't do something, if you try to access a pin that your model doesn't have or something like that. And we use that bank of information to provide this command line tool. So regardless of what model Pi you're on, it will show you the pinout for that particular device, and a little ASCII art diagram of the Pi itself. You can also request to look at other models by looking up their revision code and seeing what the pinouts or what the spec of one of the other devices is, one of the other models. And so one of the most popular hats out there is one that we make called the Sense Hat. We made this especially for an educational program. There are 2 Raspberry Pis on the International Space Station with one of these sensor boards attached. And they're in these great space-grade aluminium cases. They went up with British astronaut Tim Peake for this Astro Pi mission. This was an opportunity for children in schools in the UK and later all around Europe to write code in Python which would be run on the space station. The board has a bunch of sensors, so you can look at the temperature, pressure, humidity, pressure, accelerometer, gyroscope, magnetometer, and there's an LED matrix that you can program, and there's a little joystick that you can use as input as well. So it's a really great board for all sorts of different purposes. So it just goes on the Pi directly like that. That's what I was talking about hats earlier. So just a couple of examples. So you can scroll text across these the LEDs. You can scroll text across it, or show letters, or show information on there, or just arbitrarily access the pixels individually and make your own patterns and icons. You can easily get access to the sensor data just by reading the properties on the object, and you can do stuff like this where you show a value of one of the sensors in terms of which LEDs are lit. So have a kind of a bar graph, if you like, of LEDs according to something like the temperature or the humidity. And so the Astro Pi program will be in its 3rd year this year, and we'll be on our 3rd astronaut that's run the program. So Tim Peake from the UK, Thomas Pesquet from France, and then there'll be another European astronaut running the program in the next term. So this is a competition that anybody, any kids from schools in Europe can enter, and there's various different levels of what they can do. They don't have to do anything too complicated, but anything from tiny little scripts which interact with the astronauts, or show them messages, or read the sensors and tell them something, or a game that they can play, or something that they can interact with. We've had some really interesting entrants, and some of them are doing some really cool sort of science experiments and actually logging the data and then running the experiments again at home to compare the results and actually thinking about space. We actually have 2 emulators for this. This is one of the things we did to try and engage more people into the program, actually, without having to buy Raspberry Pi, without having to buy SenseHats, or even if a classroom only has 1 or 2 the real hardware they can use, the rest of the class can participate in this. So on the website trinket.io, which is really great on its own for doing Python stuff in the browser. There's actually a special mode of it that if you import the SenseHat module, it brings up an emulation of what the SenseHat looks like, and you can program the LEDs using exactly the same API, or using their Python in the browser. You can also use the sliders. So this is a really good way of just testing your code as well, that if you write some code that says when the temperature gets over 80 degrees, this should happen. There's no way of easily sort of getting your Pi to read over 80 degrees, so in order to just test it, you can do something like this. There's also a desktop emulator that comes in Raspbian, but you can really this on your PC as well, run it offline. Again, you can access the joystick and the sensors and control the LEDs. Really good way of testing your code out and having a go at doing something like a science experiment without having access to the hardware. So you can enter the competition with just having used this freely available software, or the Trinket web service. The Pi camera is one of the other really interesting things about the Pi. So the Pi has a CSI port for connecting up a camera module, because the Pi originally came from a mobile phone chip, and it had access to 2 cameras for the front and back-facing camera. And so using one of the sort of camera modules you would get in a mobile phone, you can actually access the camera, do photo and video in 1080p, full HD photography, but actually use your programming to control when pictures are taken or change the configuration and settings in real time according to sensor data and things like that. There's a basic command line interface that you can use and a brilliant Python library that has a really nice API for controlling the camera. As an example, just some Python code that would capture an image and record video. And if you want to hook it up with some GPIO components, say wait for a button to be pressed before taking a picture, again, it's just very straightforward. It should feel very familiar if you've used any sort of Python APIs before. There's a lot of interesting stuff in the library that you can access that the PyCamera gives you that are really interesting to play with. So there's a whole list of image effects that it allows you to use, so you can kind of do interesting stuff like this. Use all these different image effects, and you can also stream over the web quite easily. So one of the recipes in the PyCamera documentation shows you how to do this, and there's a sort of more complex version in this GitHub project there's a really interesting way of being able to stream your camera footage over the web. This is the second project that I have on the Pi that's connected to my Tortoise table. And there's a lot of people doing really interesting stuff with PyCamera and OpenCV. So this blog, pyimagesearch.com, is full of tutorials and setup guides and things on how to do facial recognition and object recognition and actually learn about that kind of area using the Raspberry Pi and OpenCV using PyCamera. So do take a look at the documentation for some of those projects. The GPIO docs are on Read the Docs, and you've got the SenseHat library, and SenseEMU is the desktop emulator, and then PyCamera as well on Read the Docs. They all have really good documentation. We have a magazine called the Magpie. You may be familiar, and we once gave away the Pi Zero came sort of on the front cover of the magazine. It was the first time a computer magazine had ever given away a free computer with the magazine. And we do some really interesting stuff with the magazine as well. It's out every month, and there's projects and articles and interviews and things, 100 pages every month, and it's really great. But we do some really interesting things like the giveaway with the Pi Zero, and one of the things we did recently was we teamed up with Google, and they put together they made a hat called the Voice Hat, and you've got this cardboard foldable container that you put the Raspberry Pi, the hat, and a speaker inside. It has a big button on the top, and you essentially make your own, sort of Google Home Assistant. So you can speak into this and have it process your thing. Use the Google Assistant to give you an answer the same way you would ask your phone or ask your one of these devices at home. Ask it a question or ask it to use something, some web service or something. But you can also write Python code which processes the commands, the voice commands, and you can use custom commands to do stuff, which could include, say, GPIO stuff or camera stuff. So turn the lights on or make the robot go forward, take a picture, that kind of thing. So some really interesting projects people have been doing with that recently. And you can check out the stuff on our blog and in the Magpie's blog, and some follow-up articles in the Magpie as well, and on the AIY Projects website. That stands for AI Yourself, Artificial Intelligence Yourself. It was a really great project that Google did. So one of the things I just want to mention briefly is is a little side project I've been working on. I gave a lightning talk on it yesterday. You can check out my slides online. Is that based around the problem that PyPy doesn't support uploading ARM wheels. So when you so Python wheels, if you're not familiar, the way of providing pre-built binaries for your Python packages, and you can upload pre-built versions to PyPy, but if they're written in C, then they have to be when they're built, they're compiled for the architecture that they were built on, and so you have to provide one for each type of architecture you want to support. Windows 32, Windows 64, Mac, Linux 32, 64, and so on. And ARM is a completely different platform. So, even though you can actually build wheels for ARM that run on the ARM architecture yourself, you can't distribute them easily using PyPI. So what I've done is written some software which automates building of all these of all the packages on PyPI and provides them in a repository that you can install from. So yeah, check out the more details in my speaker deck, or come and speak to me about it if that sounds interesting to you. So there's lots of different ways you can get involved in all the stuff I've been talking about. So one of the great things is, you know, if you have Raspberry Pis at home, or if you choose to buy them, you know, anything you do with it, I mean, making projects or just learning stuff yourself, or getting into you know, the electronic side and the physical computing side is really great. And we love to see more people learning in, you know, things that they wouldn't otherwise be learning, and actually doing some really interesting stuff. You can also contribute to some of these libraries that I've been talking about. It'd be great to have some more eyes over, cast some more eyes over some of these projects, and help other people upgrade their modules to Python 3. That's a real problem for us sometimes in the education world, when we're trying to use Python 3 and we end up getting stuck and having to go back to Python 2 for a specific module that hasn't been ported. There's been some really interesting open source projects and Python libraries for Raspberry Pi, things like PyCamera. So yeah, anything like that you're interested in making, you know, we can end up using in our educational resources, because that's where the inspiring projects come from. So yeah, do take a look at the source code for some of these libraries, and if you want to take a look at contributing, that would be really great. As I say, I mentioned the Magpie. So this is a magazine you can buy in the shops, but you can also download for free. It's one of the things we do, try to get our stuff, the stuff that we do, the educational programs, the hardware and the software, out to as many people as possible. That's why we write the emulators. It's why we provide the x86 image of our distro. We provide free PDFs of the Magpie as well, and we do a series of books that we also sell. And we encourage people to try and pay for them if they're able to, because it helps fund our educational programs the same way the Raspberry Pi sales help. But you can also download them for free, so they're freely available. If you want to run workshops, you want to go and do something like this in the community, this kind of thing is really great, a great resource, as well as the resources on our website. So one of the things I'm involved in a lot lately is the network of Raspberry Jams. So these are free community events that anyone's allowed to set up, so they're completely independent from the foundation. We just promote and support them. There's a lot of family-friendly events, so they're not necessarily kind of tech user groups, like maybe you have Python user groups at home. But some of them are, which is great as well, but a lot of them are sort of focused around not just kids learning, but for anyone to get access to having a go and learning some programming skills and learning about technology through digital making. There's a guidebook available that I put together that helps people start their own Raspberry Jams, and you can contact me about setting one up as well and get some support from us. So do take a look at the Raspberry Jam page on the website, which has a map of where all the jams take place around the world. So have a look if there's one near you, or if there has been one near you, and maybe you could go along to it, or if you have kids, take them along to it and learn with them and actually work together. There's some really interesting stuff that you see a lot of families doing together at these events. And Danielle will be pleased to see a few of those in Africa as well. So Code Club, as I say, is one of our projects. So this is a really easy way of doing some volunteering that has a really big impact on local children. So if you have kids in school, you can go along to their school and say, I'd like to run a Code Club. There's projects provided, so you don't have to come up with your own, you don't have to write your own materials. You can use some materials that have been created by educators at the foundation. There's training support provided. And if you just want to try and do your bit to try and help kids learn, that, you know, write their first lines of code and do some really interesting projects, then this is a great way to get involved. And there's information on the Code Club World website about the different initiatives in different countries around the world. We also provide a means for you to contribute translations, so we can actually reach more people with our materials as well. So that's something, again, you get involved with. And that's all. Thank you very much.
All right, thank you very much for the talk. We have a few minutes for questions, so any questions?
Do you know off the top of your head of any specific projects that need help porting to Python 3?
There was one that was my go-to one that's just been ported, which is really good news. I can't think off the top of my head. We're getting better, aren't we? So that's good. We should perhaps make a sort of Hall of Shame type thing for Raspberry Pi specifics, but okay.
Do you know of some industrial projects, including the Raspberry Pi, or would you recommend to do that?
Yeah, we sort of sell Raspberry Pis into three main markets. The industrial market, where people are using them in automation in factories and things like that, into the hobbyist community, people making projects at home, sort of thing you'd see at Maker Faire, and into education. So three very distinct and very interesting communities. In industry, you see, so we actually use Raspberry Pis in the Raspberry Pi factory to test Raspberry Pis. So as they come off the production line, there's a Pi that just does a basic electronic test to make sure it's come out right. Arduino actually do the very same thing. So they have a Raspberry Pi at the end of the production line, and they do some electronic test on the Arduino to do the same thing. And we see other people doing similar things with their own products. You see a lot of people actually building a product around the Raspberry Pi, either the single board computer that you would buy, the $35 one, or the industrial compute module that we provide, which is a Raspberry Pi chip in a sort of embeddable form factor that you can build your own I/O board. And you know, if you're building a smart TV or something and you want it, you want a well-supported sort of Linux platform in the TV, then you can build a baseboard and have as many HDMI ports or whatever else it is that you want, and put them in exactly where you want them, build your product around it, and then buy the compute module and just slot that in, and you've got sort of all of the hardware support of Raspberry Pi for free. So there's lots of people doing things like that. So one that comes to mind is a big company called NEC, who make big stadium TV displays. They're actually shipping 70, 80, 90, 100-inch TVs with the compute module embedded inside them. And one of the things about that is that you can design a board like that for today's Raspberry Pi, sort of whatever the model is at the time, and any future upgrades of Raspberry Pi, when the compute module becomes available, you can start shipping those ones instead without having to change anything. So it's just it's actually a SODIMM like RAM connector. So the device, the module, just slots in to a baseboard that supports that sort of well-supported hardware component. Yeah, there's lots of things like that. Yeah.
Okay, we have time for one more quick question.
An extension to the last question, what about real-time programming with a Raspberry Pi? I guess with Linux and especially with Python, you are not able to fulfill hard real-time requirements. So is there any alternative that you know is typically used, or are there plans in this direction, or is this completely out of scope?
No, so there's definitely a ways that you can use a Raspberry Pi in a project where you need the real-time you need real-time stuff. So a good way of doing that is pairing it up with something like an Arduino. So if you sort of want to be able to write your programs in Python and or something like that, something high level, or maybe they talk to some web services, or do something like that that you couldn't necessarily easily do with an Arduino on its own. But actually write all that logic and all that programming on the Raspberry Pi, but then send off the bits that you need doing real time to the Arduino or any microcontroller. So that's something you see a lot of people do, is they say like, oh, I did all this, this, and this in the Raspberry Pi, but the such, the things like NeoPixel grids or something where you need precise timing, and if you've got like loads of other programs running, there's a chance that the timer will go off or something. Whereas ship it off to an Arduino, tell that what to do, and let that do the sort of heavy lifting on that part of the project, but actually still controlled by all this stuff and written in high-level languages like Python on the Pi. So that's one option. A lot of people prototype with stuff like this as well, and then perhaps they'll do a proof of concept using a Pi, but then the real product will use something else. So there's a few different options. Yeah.
Okay, we're out of time. Thank you very much for talking in.
Okay.